Today we're diving into a paper titled REFT, Reasoning with Reinforced Fine-Tuning, which explore a novel approach to enhance the reasoning capabilities of large language models. The paper focuses on math problem solving, a task that requires complex reasoning skills. What's the main challenge that this paper addresses?
The paper tackles the issue of limited generalization ability in supervised fine-tuning SFT methods for reasoning tasks. Traditional SFT approaches rely heavily on the provided chain of thought annotations, which often represent only a single correct reasoning path for a given question. This can lead to models that struggle to generalize to unseen problems with different reasoning paths.
So the paper proposes a new approach called reinforced fine-tuning, REFT, to address this limitation. Can you explain how REFT works?
REFT combines supervised fine-tuning with reinforcement learning, RL, to improve generalization. It starts with a warm-up stage where the model is initially fine-tuned using SFT on a dataset of question-caught pairs. This provides the model with basic problem-solving skills.
And then the RL component comes into play. How does REFT leverage RL to enhance reasoning?
After the warm-up, REFT employs an online RL algorithm, specifically proximal policy optimization, PPO, to further fine-tune the model. PPO allows the model to explore multiple reasoning paths for a given question by sampling different caught annotations.
So instead of relying on a single annotated path, REFT encourages the model to explore a wider range of reasoning strategies. How does the model learn from these explorations?
The model learns through a reward-based system. The reward is determined by comparing the answer extracted from the generated caught with the ground truth answer. A correct answer receives a reward of 1, while an incorrect answer receives a reward of 0. This simple reward function provides clear feedback to the model, guiding it towards generating more accurate reasoning paths.
That's interesting. So REFT essentially learns from its mistakes by exploring different reasoning paths and receiving feedback on the correctness of its answers. Can you elaborate on the specific benefits of this approach?
REFT offers several advantages. First, it significantly improves the generalization ability of the model compared to traditional SFT methods. This is because REFT learns from a wider range of reasoning paths, making it more adaptable to unseen problems.
That's a key advantage. Are there any other benefits of using REFT?
Yes. REFT also benefits from the fact that it doesn't require additional training data or a separate reward model. It leverages the existing training data and uses a simple reward function derived from the ground truth answers. This makes REFT a more efficient and practical approach compared to methods that rely on extra data or complex reward models.
That's a significant advantage in terms of resource efficiency. The paper also mentions that REFT can be combined with other inference-time strategies like majority voting and reward model re-ranking. Can you explain how these strategies work?
Majority voting involves generating multiple caught annotations for a given question and selecting the answer that appears most frequently. This helps to reduce the impact of individual errors in the generated reasoning paths.
So it's like a democratic approach to decision-making where the most popular answer wins. And what about reward model re-ranking?
Reward model re-ranking involves training a separate reward model to evaluate the quality of the generated caught annotations. The model then ranks the generated caughts based on their predicted reward scores, and the highest ranked caught is used to extract the final answer.
So the reward model acts as a judge, evaluating the reasoning paths and selecting the best one. The paper presents experimental results on several data sets. Can you summarize the key findings?
The experiments demonstrate that REFT consistently outperforms SFT on various math problem-solving datasets, including GSM-8K, SVMP, and MathQA. REFT achieves significant improvements in accuracy, particularly on problems that require complex reasoning.
That's impressive. The paper also explores the use of REFT with smaller language models. What were the results of those experiments?
Even with smaller models, REFT still outperforms SFT, indicating that the benefits of exploration and reinforcement learning extend to models with limited capacity. This suggests that REFT is a robust approach that can be applied to a wide range of language models.
That's encouraging. The paper also includes an ablation study to analyze the impact of different components of REFT. What were the key takeaways from that analysis?
The ablation study highlights the importance of the partial reward mechanism and the Lowej divergence constraint in REFT. These components help to guide the exploration process and prevent the model from diverging too far from its initial training.
So these components play a crucial role in ensuring the stability and effectiveness of REFT. To wrap up, can you give us a quick summary of REFT's key contributions?
REFT introduces a novel approach to fine-tuning language models for reasoning tasks, combining supervised learning with reinforcement learning. It improves generalization ability, reduces reliance on additional data and complex reward models, and achieves state-of-the-art performance on math problem-solving benchmarks.
This was a good discussion on the key points of REFT.